This is AP Calculus AB, lesson 1-4. We're talking about continuity at a point. So this is where we are in the unit guide. We're on our last standard B limits, and then we move on to continuity. It might seem that continuity at a point should be continuity, and I think the reason I'm going to call it limits is just because we use limits to prove this, and then we'll get more into continuity. Maybe this should be both B and C here to be a little bit more formal. All right, linear. Whoa, they look like a line, right? So let's go ahead and make a line just right here. So continuous, the way that I like to think of it is that it is missing things. It doesn't have these four things. And let's write this on the side notes, just how to think about continuity. Continuous, go back to green here. Continuous means that you don't have, so you have none of these 4 bullet points. Breaks, gaps, holes, or VAs. What do VAs stand for again?
Vertical asymptotes.
Yeah, thank you. Vertical asymptotes. Very well. So breaks and gaps might, and maybe even holes, might sound like the same word to you. I can briefly explain that. So breaks just mean they just totally stop, and then there's nothing over here. A gap means I have a function that just skips a point and continues over. This is a gap. A hole means I have a function that has a tiny little hole in it and then continues on, very similar to a gap. And then vertical asymptote, we know what that looks like. It goes upwards towards infinity because there's this VA here. So it can't have any of those things, and if none of those things are in it, then it's continuous. So tell me, arrow, do you think linear functions are continuous? Yes or no?
Yes.
Yes. So a linear, right, continuous everywhere. And we're going to abbreviate saying continuous as CONT. It might seem like it's continued, but it's continuous when you're in calculus. So it's continuous everywhere. WHERE. Quadratic. What do quadratic graphs look like again? Can someone explain? Yeah, parabola. So I'm just going to do, let's do an upside down parabola, concave down. So this is a quadratic. Ben, what do you think? Continuous or not continuous?
I think it's continuous.
It is, yeah. So this is also continuous. And it's not only just continuous. Well, yeah, I'm just saying all quadratics are continuous everywhere. Everywhere. That means everywhere on the quadratic function, there are none of these things. Cubic. What do cubic functions look like graphically? Does anyone know what cubic functions look like? It is like that, yeah. So cubic function, I will do my best interpretation of arrows. It looks like woo, 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 like this. And then this one goes up and up forever. This one goes down and down forever. So that would be a cubic function. And what do you guys think? Continuous or not continuous? Continuous. Yeah. I mean, the pattern is becoming pretty clear here. When we're talking about polynomials, they should be continuous everywhere. And cubic, this means you have something like your highest degree polynomial, your highest degree term is x cubed. Quadratic, that was like x squared, and linear was just x. Those were the highest degrees. So n beyond means I could have x to the power of, I don't know, 102. That thing is still continuous. It could be x to the 102 minus 72x to the 99. As long as it's a polynomial and it doesn't have any rational part, it's not a rational function, it is going to be continuous everywhere. So this is going to be continuous everywhere. And if that wasn't clear enough, you can add an additional note in your notes that just says polynomials are continuous everywhere. And maybe I think for the sake of just having it in the notes to look back at for the digital version, I'm going to do a giant star and say that in general, polynomials are continuous everywhere. And I should have had straight lines, but that's okay. So if I do a star and it's in red, or either or, that means that has to be in your summary. Polynomials are continuous everywhere. That was a big takeaway. Let's talk about continuity of different types of functions. So let's talk now about, oh, sorry, I totally skipped. Are we okay to move on to the next slide?
Yeah.
All right. So let's talk about the continuity of continuity. Let's do rationals. So I'm just going to do RAT. I like to abbreviate. And if you don't like that, you can say rationals. Things that have fractions. Okay, so let's look at just an example graph here. I'll put this guy right here. Nothing really that we can label about this guy aside from the fact that I'm going to be drawing my own type of function. So this function has a vertical asymptote there, horizontal asymptote there, and kind of the same thing goes like that. All right, so continuous or not continuous? Not continuous, yep. And if I were to mark a point on the x-axis to mark where that vertical asymptote was, we could say, hey, that's where it's discontinuous. So we're going to say, we'll do this in green. Hey, look right there. At this x-coordinate, discontinuous. And for my class, I'll be asking you, well, what type? Because there's 4 things that can cause it to be not continuous. So why is this not continuous? What would you say? You guys can just shout it out. What?
There's a vertical asymptote.
Yeah, discontinuous. And you can say because. I love abbreviating because VA. All right, let's look at another one. Another type of rational function that you might encounter in the jungle of mathematics looks like this. All right, so I'm going to already tell you that there's a discontinuity. So we'll say again, right there, discontinuous. And arrow, why is this one now discontinuous?
I guess it might have a gap, but I figured that I'd go right. So,
It's okay. I'll go over it more in depth in the next lesson. It's not a gap, so it was a good guess, though.
Isn't that a vertical asymptote again?
It's another vertical asymptote, yep. Because VA. Let me give you another one. I guess we can just do 4 of these. I guess in retrospect, I could have just done all 4 of the examples. That would have been better. I'm always learning how to improve these notes each time. So let's do something that looks like that, but let's see, do I have a tool that has an ellipse and inside shape is white? Like that. Cool. I'll go back to lines for when I need those. All right, so this one is discontinuous again. Why?
Because it has a hole.
Yep. And I'm going to say because hole. And what we can do is we can actually add to this graph up here. We can make it discontinuous for multiple reasons. So remember, breaks, gaps, holes. It's also discontinuous, this second graph up here, right there. So if there's 1, it's discontinuous. You don't need more than 1. But if it's 2, it's like even more discontinuous, I guess. So discontinuous. Why now? There's a new reason. So it's one that we haven't used before. So it's not a vertical asymptote, and it's not a hole. That means it's either a break or a gap.
probably break.
You're right. It is. Yeah, because break. It just stopped. You're not allowed to just stop. You have to go forever and ever. You're a function. And then, of course, our last one is going to be a gap. So let's find a cool graph of a gap. Let's go something that looks like a parabola. And then maybe, I guess I could have used a line tool. So this guy is also discontinuous. Because gap. And can we please put like a bubble around this one, like a little cloud or something, and a little cloud around this one? Okay, my cloud drawing skills obviously need to be improved. But both of those clouds don't really belong in rationals, but everything else here can be done in a rational. You can see this vertical asymptote. You can see holes when you talk about rationals. You can see this type of vertical asymptote when you talk about rationals. You don't really see these with rationals. You see those two when you're talking about a different type of function. And
Is that the piecewise function?
it is a piecewise function, yep. I was wondering if I should do a whole new slide of that. And I'm just going to do like a half slide, I think, for this one. And we have the pictures for those. So if we could label both of those piecewise, that would save us some time for the pictures, and we can just talk about the formal definition in a sec. So this is going to be piecewise for those clouds. Maybe I can do piecewise in a cloud too to make it match. When you get piecewise, then you can get breaks and gaps. And you can still get the other types in piecewise functions, because maybe one of the functions in your piecewise function is irrational. So then you could have all the different types, right? All right, so let's talk about formally now piecewise functions with the instead of calling this piecewise function, since we already labeled it, I'm just going to call this one a continuity test. Okay, on the AP exam, they will sometimes ask, actually a lot of the times on the free response, one question will ask you, prove that the function is continuous. And it'll almost always be a piecewise function. So in parentheses here, I'm going to say piecewise function, because if they ask you to prove that a function is continuous when it's a polynomial, it's kind of pointless. They'll never ask that piecewise. All right, so, and this whole thing is pretty important. So proving continuity. And this is going to be with the continuity test. There are 3 elements to this proof. All right, here's the first part. You can go ahead and copy it down with me. The limit of whatever function I'm trying to prove that it's continuous, the limit as x approaches some point, the point that I'm testing, I'm just going to call that c, from the left, has to be equal to the limit of that same function as I approach the same point, but now from the right. So the left limit has to be equal to the right limit. I'm going to pause there because I want to come back and finish the third part. This also has to be equal to something else. All 3 of these have to be equal to each other. But let's just talk about what this means right here. The left and the right have to be equal to each other. That means, and we've already seen this on the homework too, this is the limit as I approach this, I'm going to call this point C. This limit as I approach C from the right-hand side is not equal to the limit when I approach it from the left-hand side. So I've already broken with my continuity. It is discontinuous because the limit from the left does not equal to the limit on the right. That's what this means right here. But on these questions, so if this was C right here, this point right here, coming from the left and coming from the right, it does approach the same height. So far I'm okay. But it also needs to satisfy a third condition. It needs to be equal to f of c. How do I read f of c without saying f of c? What does this really mean?
The height of C.
The height of c, exactly, yeah. So down below here in green, I'm going to write this a new way. So left limit equals right limit equals height at the point. You probably are thinking to yourself, Mr. Sindel, you showed us this problem, but it does equal the height here. The height is met. When will you ever have the first 2 conditions being met without meeting the third condition? Would you like to see when that happens? When these two are met, but this one is not met?
Yeah.
All right, go back to this example right here. This is your C.
Oh, if there's a hole at that point.
If there's a hole at that point, it doesn't work. Because what is the height at C?
Does not exist.
It doesn't exist. There is no height. And even better, I could have done this. Now there is a height. At C, the height is up here. But is that height equal to the left limit and the right limit?
No.
No. So that's another way to break it. So all three of these need to be satisfied. Cool. We're almost there. I want to do some examples. Let's just do one, and then we can call ourselves good. So example. I'm going to give you a piecewise function, of course, because otherwise it's going to be way too easy to prove it. Let's do f of x is equal to, we'll do two parts. The first equation is going to be x plus 2. And that will happen if, so I'm going to do my comma, if, and some people do write if, but commas are faster to write, x is less than or equal to 2. My second equation is going to be x squared. And that's going to be if x is greater than 2. All right. You might want to jump ahead and start doing this, and you probably could. You could probably get it correct, but I want to define some terminology so that we can talk about math correctly. And again, this is where I get a little bit cutesy. If you talk about these words with other calculus students, they'll just ask you, what the heck are you talking about? I'm going to call this point the suspect point. This is our C that we had from our previous slide. X approaches C from the left, C from the right, f of C, the height at C. That is our C. Our C is our suspect point. And then what else do I want to say? These are the two pieces, I guess. So this is less important. The suspect point is the most important thing I want to take away for vocab. But these two things, I'm going to call these the pieces. So x plus 2, is that the left piece or the right piece? Is x plus 2, this top piece, is that the left or the right piece?
Left.
Left. Why?
Because it's extending all the way to the left from x equals 2.
Yeah, so it's less than, so it's going to the left. And then this one is to the right. Perfect. All right, so what do we need to do to prove that this function is continuous? We need to prove that it's continuous or prove that it's discontinuous. Either way, we're using this continuity test. So let's go ahead and write it out. I think this is the way that I want to write it to go slow. And once you get faster, you can just start abbreviating without skipping the cutesy stuff. I'm just going to say left. Maybe I should do this in black. Sorry. I want to say left. That needs to be equal to the right. And that needs to be equal to the point. The fastest way to just make sure you have this memorized is just to memorize this thing. Okay, left. Now I need to be formal about my mathematics. The limit. So tell me what to write. It's going to be
Limit f of x as x approaches 2 from the left.
as x approaches 2 from the left. Perfect. Arrow, you do the next piece. This should be equal to,
Should be equal to limit of f of x as x approaches 2 from the right.
perfect, yeah. And then I'll do the third piece. And that should be equal to f of 2. Haha, I got the easiest one. That should be equal to the height at 2. Now we actually have to calculate these things. So step 1 was just using, recalling what the continuity test was. Step 2 is actually making it formal, and maybe you can just skip to step 2. And then step 3 down here is actually evaluating. So plug in 2 from the negative side. From the negative side, that means I'm going from the left. Plug in 2 to this left piece. 2 plus 2, this thing is equal to 4. Ben, you do the next one. Arrow, you're going to do the right one. Ben, what is the limit of f of x as x approaches 2 from the right? Tell me what you're doing, not just the answer.
So, since it's approaching 2, I'm going to plug in 2, and that's 4. And
Are you plugging in 2 to the left piece or the right
to
piece?
the right piece?
Okay, to the right piece.
X squared, so that's 4.
That's 4, perfect. Arrow, talk to me about the height at 2. How do I find that?
No, because there's nothing to plug in. It should be.
But there is. You have to be careful about these signs right here. I either plug into the left piece or the right piece. Which one should I plug in at 2, at where I'm equal to 2?
The top one has an equal sign in it.
Yep, the top one has an equal sign, so
Yeah, okay, plug it into the top one.
plug it into the top one and you get
4.
4. Because all 3 of these are equal to each other, we can conclude, therefore, you guys know the symbol for therefore?
No.
Therefore, and we can make a note on the outside, this thing means therefore. I just love speeding through the math with abbreviations. This means therefore. Therefore, did I spell that? I think that's right. So therefore, f of x is continuous at x equals 2. And the second line, and thus, because that was the only suspect point, there were no other suspect points. So if that one suspect point has been taken care of, it's continuous everywhere, and thus continuous everywhere. Because these are both polynomials. We know that everywhere on this one is continuous and everywhere on this one is continuous because of our first slide. They're both polynomials. The only way it's not continuous, if it's not continuous, is if the suspect point doesn't satisfy this theorem, this continuity test. And because it does satisfy the continuity test, it's continuous everywhere. So we have to say both things. That ends the notes. If you want to add extra stuff into the notes, like we had to plug into the top for this one, you can add that in case you might have trouble remembering that later. These notes are for you. You are going to be looking back at them. I know that our last class we didn't really look back at our notes and use our notes very much, but AP Calculus is pretty hardcore where we're going to be. This stuff is being tested for the AP test. Are you going to remember to plug the suspect point in May?
Well, clearly I don't even remember now, so.
Yeah, so, all right. Make sure that you have good notes. Go ahead and write your summaries now.